Welcome to Master Mathematics in Minutes. Today's topic is about the identity matrix, and we'll cover a couple of examples on how to compute using the identity matrix. And we'll conclude the topic with a summary. And finally, be kind and subscribe for more videos. So, what is an identity matrix? An identity matrix is a square matrix of order n by n, for example, with ones on the diagonal and zeros elsewhere. Let's take a look at a couple of examples. We have an identity matrix of order 2 by 2, and with ones on the diagonal and zeros elsewhere. And for a 3 by 3 identity matrix, again, we have ones on the diagonals and zeros elsewhere. And for a 4 by 4 matrix, it's the same concept as well, with ones on the diagonal and zeros elsewhere. The determinant of an identity matrix is always 1. So we'll look at a couple examples, which will demonstrate that later. And consider a matrix A. If we were to multiply that with the identity matrix, it will return itself matrix A. So we have A times the identity matrix I, that will return A itself. Or the other way around, the identity matrix multiplied by A, and that will return A itself. So remember, it's important to check whether these two matrices can be multiplied by checking the order of these two matrices. So these identities will be dependent on whether you're able to multiply these two matrices together. And thirdly, with matrix A multiplied by the inverse of matrix A, that will give us the identity matrix itself. So with A multiplied by the inverse of matrix A, that's equals to the identity matrix, or the other way around, A inverse multiplied by A is equals to the identity matrix as well. So once again, it's important to check the order of these two matrices to determine if you can multiply these. And the inverse of the identity matrix I is itself. So the inverse of the identity matrix I is equals to the original identity matrix. We'll cover a couple examples which will illustrate all these 4 points. In the first example, we're asked to calculate the determinant of the matrix I, or the identity matrix. So the identity matrix is one where we have ones on the diagonal and 0 elsewhere. And so the determinant of the identity matrix I is equal to AD minus BC. So if A is 1 multiplied by D, which is also 1, minus B, which is 0, multiplied by C, which is also 0. And that simplifies to 1. And this confirms one of the concepts that we saw earlier, where the determinant of an identity matrix is equal to 1. In the second example, we're asked to find matrix A multiplied by the identity matrix I. So we saw earlier that that should return the original matrix A. So we will perform an example now to show that. So with matrix A and the identity matrix of order 2 by 2. So to multiply these together, we'll need to determine the order of these two matrices. So with matrix A as 2 by 2, 2 rows, 2 columns, and matrix I as 2 rows and 2 columns as well. And because the number of columns from the first matrix is equal to the number of rows in the second matrix, we're able to multiply these together. And the combined matrix AI will have the number of rows from the first matrix, which is that 2, and the number of columns from the second matrix, which is that 2. And so we're able to multiply these together. So with A multiplied by I, again, we'll multiply the row elements against the column elements. So with 1 by 1, which is 1 by 1 here, 15 by 0, which is that 15 by 0, and we'll sum these two together as a second step. And The second entry is where we'll multiply this row with the second column. So with 1 by 0, which is that 1 by 0, 15 by 1, which is that 15 by 1, and we'll sum these together. And we can populate all these for all the other entries of the matrix. And that simplifies to 1, 15, 17, and 20, which is identical to the original matrix A. And so that is equals to A. And so this again proves the concept that we saw earlier, that if you have a matrix multiplied by an identity matrix, that will return itself. In the third example, we're asked to find I times A, or the identity matrix multiplied by a matrix A. So we're given these two matrices here, and once again, we'll need to check the order of these two matrices. So we have matrix I as 2 by 2, 2 rows, 2 columns, matrix A as 2 rows and 3 columns, 2 rows and 3 columns. So because the number of columns of the first matrix equals the number of rows of the second matrix, we're able to multiply these. So the combined matrix is IA, and the number of rows is from the first matrix, and the number of columns is from the second matrix. So we have IA as 2 by 3. So matrix I multiplied by matrix A is equals to, again, we'll multiply the row by the column. So we have 1 multiplied by 20, which is that 1 multiplied by 20, and we have 0 multiplied by 50, which is that 0 multiplied by 50, and we'll sum these together. That is the first entry. So we'll pick this entry, for example. So this is on the second row, first column. So we'll take the second row of this multiplied by the first column of this. So we have 0 by 20, which is at 0 by 20, 1 by 50, which is at 1 by 50, and the second step is where we sum these together. So we can go ahead and populate all these entries, and that simplifies to 20, 48, 50, 30, and 10. And that is conveniently the original matrix A, and so that is equals to A. So again, it's the same concept as we saw earlier. An identity matrix I multiplied by matrix A will return the original matrix A. In the fourth example, we're asked to show that A multiplied by the inverse of A is equals to the identity matrix I. So we're given A and the inverse of matrix A, and the first step is to check the order of these matrices. So with A as 2 by 2, A inverse as 2 by 2 as well. And because the number of columns in the first matrix equals the number of rows in the second matrix, we're able to multiply these together. And so the resultant matrix is A multiplied by the inverse of matrix A, and that is 2 by 2. The rows from the first matrix and the columns from the second matrix. That gives us 2 by 2. And so with A multiplied by the inverse of matrix A, again, we'll take the row multiplied by the column. So with 2 by 2, which is that 2 by 2, 2 by minus 1.5, which is that 2 times minus 1.5, and we'll sum these together. And we can populate all the other entries. And that simplifies to 1, 0, 0, 1. Or in other words, an identity matrix of order 2 by 2. And so we've shown what was asked in the question. And it proves the concept that we saw earlier as well. In the final example, we're asked to calculate the inverse of matrix I. So we're given a 2 by 2 identity matrix. And so, to calculate the inverse involves 3 steps. That is equals to 1 divided by. Step 1 is to calculate the determinant of the matrix, which is A, D minus B, C. So if A as 1, multiplied by D, which is 1, minus B, which is 0, multiplied by C, which is also 0. And step 2 is where we swap the positions of A and D. And step 3 is where we put a minus sign in front of B and C. So 0 becomes 0, 0 becomes 0. So it's the same zeros despite taking the negative. And so the determinant simplifies to 1, and we'll copy that matrix down, and that is basically an identity matrix of order 2 by 2. So this proves one of the concepts that we saw earlier, that the inverse of the identity matrix is itself. To summarize, we've discussed the identity matrix. An identity matrix is a square matrix of order n by n, for example, with ones on the diagonal and zeros elsewhere. So these are a couple of examples on what an identity matrix could look like. A 2x2, a 3x3, and a 4x4. And we saw that the determinant of an identity matrix is always 1. And we also saw that if we were to multiply a matrix A by the identity matrix I, that returns itself. Or the other way around, I multiplied by A is equals to the original matrix A. Again, we'll need to check the order of these matrices to determine if these can be multiplied. And we also saw that the multiplication of the original matrix A against the inverse of matrix A will return the identity matrix. Or the other way around, the inverse of matrix A multiplied by A is the identity matrix. Again, we'll need to check the order of these matrices to determine if these can be multiplied. And the inverse of an identity matrix, I, is itself I. Thank you very much for watching. This is Master Mathematics in Minutes.